So the first unit I always choose in my classes is the chemistry unit, because when you look at matter, you look at human beings, what we're made of atoms. Atoms interact to form molecules. Molecules interact to form cells. Cells interact to form tissues, organs, organ systems, and the organism. You might remember that from general A&P, right? The levels of organization. So whenever you're going to start a class talking about the human body, we have to have a good understanding of the chemicals that are part of this process of metabolism. So we're going to start out with biochemistry, and what makes chemistry biochemistry is it's the chemistry of living things. So all the chemical processes that we see in living things. So we're going to start out talking about a lot of organic molecules, and organic simply means it contains carbon found in living things, because like I said, a lot of the homeostatic mechanisms we have are working to maintain our biochemistry. And as a nurse, what we do at the bedside is trying to alter and change bad biochemistry or maintenance mechanisms. So that's what gives us job security right? Is broken feedback systems where the body's not able to control the balance of these chemicals. They're not making them efficiently. So a lot of times patients come in, they have some chemical imbalance, whether it's dehydration or electrolyte imbalances. We need to replace them with fluids. So some of those fluids contain ions like sodium, potassium, calcium, chloride. And understanding where they come from and how they work in the body is important for understanding why our patients need a particular fluid and why they also might be at risk for overload. If we could let a fluid run too long and we have an excessive amount of particular electrolyte, that can affect different body systems and can cause death. So it's really important that we're monitoring our fluids and not just hanging the bag and walking away, because we're impacting that patient's biochemistry. So it's good to have an understanding of what these fluids are for. And I can't tell you how many times I've had conversations in my clinical experiences where people will tell me something that demonstrates that they don't understand the biochemistry of that patient. They'll say, oh, we're going to give this patient this fluid because of this. And it's not doctors, but it's usually the treatment team sometimes misunderstands why fluids are given and why we're replacing or not replacing. And families then start to question. So as a nurse, your job is to be the liaison between the doctor and the family, right? Sometimes they're going to have questions that the doctor's not able to answer. So by you having this understanding, you're going to be able to answer those questions. So looking at chemistry then, in general, there's basic chemistry like you took in high school, or maybe you took it here on campus, that just talks about, acids, bases, metals, nonmetals, the periodic table, right? We're not going to go into that basic chemistry, but you have to have a good understanding of that to understand biochemistry. So you need to understand what an ion is, for example. And we'll talk a little bit about that and kind of review some of those. But biochemistry is, like I said, just the chemistry of living things and involves two different types of compounds. Inorganic compounds, which means they do not contain carbon. That's the key word. Inorganic compounds do not contain carbon. Inorganic compounds can be found anywhere. They can be found out in the environment. They can be found outside of living things, right? You can see we use salts for lots of different things. We can get sea salts out of the ocean. Those are inorganic compounds. But compounds like carbohydrates, fats, proteins, nucleic acids, those are organic compounds. Living cells make those compounds. So they all contain carbon. So like sugar, for example, that's made by a cell. That's assembled by a cell. We get sugars from fruit, right? From plants like sugar cane. Those are made by cells. So this is where we really focus our energy when you talk about biochemistry, is looking at how the carbohydrates, fats, protein, nucleic acids interact in the body. But they're equally essential for life, whether it's inorganic or organic. We need water. Most of our body is made of water. Most of our water in our body is inside of our cells, so that works as an important solvent for all these chemical reactions. And these ions that we get from the different salts, and we'll talk more about that. And then acids and bases affect our blood pH. Does anybody remember what the blood pH is? Very good, 7.35 to 7.45. So are we slightly acidic or slightly basic? Slightly basic, yes. So it's very narrow range, though. There's not a lot of give with 7.35 to 7.45. So if we dip into the acidic range, the body's going to be affected by that. Chemical reactions are going to be impacted by that change in pH. If we become slightly alkaline, same thing. So the body is constantly working to manage these electrolytes to make sure that we're in the right pH range. So an important inorganic compound, the most important inorganic compound in the human body is water. And what's unique about water are the hydrogen bonds that it forms with other molecules. Have you ever noticed how the little water bugs in the summertime and like this time of year even in the ponds, how they can skim across the surface of the water? That's because each little water molecule forms hydrogen bonds connecting the water molecules together, forming almost a skin on the surface. That's essential because in our lungs, that water molecule forms a film on the inside of our lungs, keeping our lungs inflated and intact. But if we have too much of that surface tension, that cohesion, that can cause our lungs to collapse. So we need just the right balance of water and another compound which we call surfactant, which is a protein substance made by the lungs, that's on your list, that helps overcome cohesion and surface tension in the lungs. Have you heard of women that go into labor too soon and they say, oh, they're giving her an injection to help develop the baby's lungs? Have you heard of that? That's surfactant that they're giving that mom, which will enter the blood, go to the baby, and will help overcome the water molecules that are forming a water droplet in those tiny, tiny alveoli of the lungs. Sometimes they'll give a surfactant mist to babies right after they're born if they're born premature to, again, help overcome that surface tension of these water molecules that want to stick together and form a water droplet. So water is very important. It has a lot of different features because of this hydrogen bonding ability. It has a high heat capacity and heat of vaporization, which means that it's able to retain or maintain its temperature. Like I can go outside, it can be 20 below. I can go outside and get the newspaper and my entire body doesn't freeze, right? If you set something else outside that's not made of a lot of water, say something that is, oh gosh, what's an example? Say a sugary substance. A sugary substance that has less water would freeze more quickly because it doesn't have that high heat capacity that water has. And we can go outside when it's 110 degrees out with high sun and high humidity in Florida, for example, and we don't melt or die of heat stroke instantly because, again, our body is made of mostly water, and it takes a lot to raise the temperature of water. So that is kind of a cushion in the environment between humans and their environment to keep their temperature the same. And water is polar. There's a diagram here that shows the polarity of water. What that means is water has two different charges within the same molecule. It's slightly positive and slightly negative. Which atoms in the water molecule are slightly positive if you look at that diagram? The hydrogens, yeah. The two hydrogens are slightly positive. So that means when we throw a salt in water that's made up of a positive and a negative metal and a nonmetal, positive, negative ion, you can see here that the hydrogen atoms that are positive are attracted to the negative chloride ion, and the sodium, which is a positive ion, is surrounded by the slightly electronegative oxygen part of the water molecule. So basically, it separates these ions from one another, so this sodium can go off and do something in the body, can leave that space and go somewhere else and do its job. And the chloride can leave its space and go somewhere else. So we're essentially separating these ionic compounds, which are salts, and allowing those ions to go off and do their work that they do. And some of those ions, open channels. If you remember this from general A&P, we have sodium channels, potassium channels, chloride channels, right, that they bind to, and they allow neurotransmitters to move through, and a whole host of mechanisms. But we need water to separate. What type of bond holds together salts? It's the strongest of chemical bonds. Do you remember that? Those are slightly weaker bonds. One step up from the covalent bonds. We're going to talk about those today. What? Say it louder. Ionic bonds, yes. Ionic bonds are strong bonds between a metal and a nonmetal. So salts have ionic bonds, and the hydrogen and electronegative oxygen and the slightly electronegative or slightly electropositive hydrogen are able to break that ionic bond and separate those ions and allow them to do their work. So we'll talk about that as we get to the different systems, but particularly in the very last few weeks of the class, we talk about fluid and electrolyte imbalances and acid-base imbalances, and that's a really critical skill to bring to the bedside because it's a big problem in a lot of our patients. So a good understanding of that is going to help you prevent that in your patient. So again, salts are ionic compounds. They're bonded with ionic bonds. And when we throw them in water, they become surrounded by these water molecules, and they're separated into cations. Cations are positively charged ions, and anions are negatively charged ions. So cations are things like sodium, potassium, magnesium, calcium. Those are positively charged ions. Negatively charged anions, the main one in the body that you'll see over and over again is chloride ion. So we call these electrolytes because they are charged particles, charged ions. They can conduct electricity. So that's why we are good conductors of electricity, right? So they always talk about in CPR classes, if you go to a scene and there's a line, electrical line down after a rainstorm, and there's people laying around injured and there was a car accident, you always assess the scene, make sure it's safe, right? You never walk into an area where there's down power lines. That's something for the fire department to take care of, because if it's laying on the ground and there's water and you step in that water, you conduct that electricity, you complete the circuit. So because of the electrolytes we have in our body, we are good conductors of electricity. So those salts, those are common salts that you're going to see in IV fluids or in medicines when we're trying to replace these. The elderly commonly have issues with electrolyte imbalances because of their kidneys are not as good at maintaining these electrolytes. So when you look at the kidneys, for example, our nervous system relies on sodium and potassium to function. So if the kidneys are failing, sodium and potassium are out of whack, and that affects the nervous system. So they're going to have issues with level of consciousness, movement, heart function because of these imbalances. So some people have to, undergo dialysis because the kidneys just aren't able to maintain those electrolytes anymore. So acids and bases, this is just a little bit of a review. These are, again, still inorganic compounds, not part of biochemistry just yet. Acids are any substance that releases hydrogen ions into solution, so we call that an acid. The more acidic a substance is, the more hydrogen ions are in that solution. So some important acids we see in the body, hydrochloric acid is a strong acid, which means when we throw that into water, it separates into H+ and Cl-. Where if we look at something like carbonic acid, some of that remains as carbonic acid, so it's a weak acid. So if I take hydrochloric acid, throw it in water, it's going to break up into H+ and Cl- into those ions. But I can reverse that arrow, and some of those ions are going to come together and form HCl. But for strong acids, a majority of ions are or a majority of that solution is in ionic form for strong acids. If it's a weak acid, we see like carbonic acid, we see the H2CO3 molecule in solution not separated into ions. So is it able to raise or lower pH then? Not if it's in that whole form. Only if it breaks up into its ions, which is H+ and HCO3-. So these are the ions. But so carbonic acid is a weak acid. Hydrochloric acid is a strong acid. Based on how much of that solution is strictly ions and how much remains still as the whole molecule determines if it's strong or weak. Okay, so acids have a pH less than 7, and the lower the pH number, the higher the hydrogen ion concentration. So the pH scale goes from 0 to 14. I'll just skip ahead here. So here we can see that for the strongest acid, which is hydrochloric acid, the concentration of hydrogen ions in moles per liter is 10 to the 0. That's a bigger number than 10 to the negative 1, right? 10 to the negative 2. These are all getting smaller because every time we have a negative exponent, that decimal is moving further and further to the left, right? Correct, I should say. So this is a much higher number of hydrogen ions compared to 10 to the negative 14 hydrogen ions. So very few hydrogen ions here at a pH of 14. So this is a strong base at 14, and this would be a strong acid at 0. Water is neutral, which means we have equal amounts of acid and base in that solution. So, for example, if you look at water, what would water break up into? What ions? Hydrogen ion, and we can't lose any ions, so OH minus is the other ion. We call that hydroxide ion. So hydrogen ion makes something base, or makes something an acid, but if you have hydroxide ion, that makes something a base. So water has equal amounts of ions that would make it either an acid or a base. It's equal amounts, so it's neither. It's neutral at 7. So it doesn't contribute either acid or base into a solution. That's why it's the universal solvent. So if you go back and look at bases, bases are hydrogen ion receivers. They take hydrogen ion out of solution. So in this case, we see the hydroxyl or hydroxide ion is another way of saying it. That negative charge on that OH minus will bind up hydrogen ion in an acidic solution and turn it into what? OH plus H equals H2O, water, and that is neutral, right? So that's a good way to get rid of acid, is to give base. So if a patient is acidic in their plasma, we will treat them with a base, sodium hydroxide, depending on how we want to treat that. Sodium bicarbonate is a popular way of treating acid conditions. You've probably done that yourself when you take a Tums, right? You're taking a base to overcome the acid in your stomach, and it makes you feel a lot better and allows the digestive process to continue. So sometimes when we get too much acid in our stomach, digestion stops because the enzymes are inhibited with that low pH, that acid, and then you just feel kind of sick, nauseous. But if you take an antacid, it raises the pH, the enzymes can do their job, and then digestion resumes and you feel a lot better. So some people have more trouble with that than others. So important bases in the body, bicarbonate ion we're going to talk about later in the semester, and ammonia is kind of a middle molecule that's formed during metabolism. Our body doesn't do well with ammonia, so we have mechanisms in place to take care of ammonia and not let it build up. We only see ammonia levels rising in people with liver failure, like cirrhosis of the liver, and then they act like they have dementia because of high ammonia levels causing their thinking, their brain not to function properly. So again, this is a pH scale. You can see some familiar things on the right-hand side there. Ranges from 0 to 14. Again, the pH scale is based on what concentration? Hydrogen ion. Hydrogen ion concentration. So the more hydrogen ion, how does that affect pH? It's like a teeter-totter. The higher the hydrogen ion concentration, what's the pH? Lower, right. The strongest acid in this scale is hydrochloric acid. It has a pH of 0. Okay, so strong acid. And 14, we would call that a strong base. Yep, yep. And then we have everything in between there. Okay, so a neutralization reaction is when we take an acid and a base, they react, they switch partners, and they form a salt and water. So sodium hydroxide here is the base. Hydrochloric acid, or hydrochloric acid, is the acid. It forms sodium chloride and water. Every time we mix an acid and a base, we get a salt, which is not an acid or a base, and water. What would the pH be of that solution on the right side of the arrow? What? What is the pH of water? 7. Because the salt is not an acid or a base, so it doesn't have a pH. The water is what contributes to a pH, and that would be a pH of 7. We have a base. It could have a pH of 14. The hydrochloric acid could have a pH of 0, but when I put them together, they swap partners. The sodium goes with chloride, and the hydroxide goes with the H to form water, and we have a neutral solution. So our bodies are constantly adjusting our ions to neutralize and buffer changes in pH. And it's a complex process. So I don't want you to think that you're going to come out of here completely understanding buffer systems, because we don't. But having just a general knowledge of how they work is going to help you, with your patients. So don't feel like you have to understand all the chemistry of that, because you can take a whole semester on biochemistry, right? Some of you may have even taken that class already. It's very detailed. Okay, so let's actually, I think we have been talking for a little bit already. Let's take a break at this point, because this is shifting gears and shifting concepts, and then we'll come back in 5 minutes, so 13 after about, and we'll pick up with this topic. Okay, so organic compounds now is our next topic. And the major classes of organic compounds are carbohydrates, lipids, proteins, and nucleic acids. And when you think of this, you're just going to be thinking of the foods we eat. The foods we take in have to contain these building blocks to maintain what we're made of. And we're made of carbohydrates, lipids, proteins, and nucleic acids. But your Snicker bar that contains carbohydrates, lipids, and proteins doesn't have these molecules in your organic molecule list in there. So when you take that Snicker bar in, your body is going to break down the peanut and all the ingredients of a Snicker bar, and it's going to reassemble them to make these important organic molecules that you need for life. So when you think organic, what makes it organic, first of all? Carbon. These are large molecules with many repeating units. Carbon, hydrogen, and oxygen are the basis of all of these molecules. You're going to find large amounts of carbon, hydrogen, and oxygen in all of those molecules. I'm not going to hold you accountable for the ratio of how many in lipids versus carbohydrates. That's more of a biochemistry class. Just be aware that they're large molecules. They are covalently bonded. They all contain carbon, and the carbons are covalently bonded. So what is the advantage compared to ionic bonds, like I said, that are very strong bonds? What is the advantage, do you think, of covalent molecules being a little weaker? Yeah, they can break apart, because isn't that the goal? When we bring our food in, we need to break those bonds, release the energy, reassemble, and make something new. So covalent bonds are weaker bonds, still giving it structure, though, but just a little easier for our digestive enzymes to act on them. So when we think about what we're making when we bring in that Snicker bar, we're making collagen, which is a structural protein that gives strength to the skin, the bone, connective tissues. When we look at nucleic acids, DNA and RNA are important for making proteins in the body. Lipids, important lipid is like myelin. Myelin is an insulation over the axons in our nerve cells, and it speeds the conduction of nerve impulses down our neuron. So making that myelin is really important. And where do we get the building blocks to make myelin? Through the food we eat that contains these building blocks. So it's what we call the process of making something smaller. Making something bigger from something smaller, we call that catabolism. Anabolism. Anabolism is when you take something smaller and make something bigger from it. So when we break apart these things and make something new, we call that anabolism. And when we digest something, we take something bigger, break it down to its bits and pieces, we call that catabolism. And we're going to talk more about that next week. So don't feel like you have to master that definition today, because we'll talk more about it and give more examples next week. So when you look at an organic compound, we call it a polymer, which is like, think of what a pearl necklace looks like, right? Many pearls in a strand. That's a polymer. So the whole thing is made up of tiny repeating units. That's the polymer. The monomer is the building blocks of that polymer. So for example, each individual pearl in a pearl necklace is the monomer that makes the polymer. Poly means many. So all of these organic compounds are polymers of smaller molecules. So to make a polymer, any organic compound, so on the left there, we have two monomers. So those could be two amino acids. They could be two monosaccharides. Any small repeating unit that makes up an organic compound we call a monomer. So if I'm going to combine those two together, the process causes a removal of water. And where does that water get removed from? If you look on the left side of the page here, we can see OH is removed from one monomer, and H is removed from the other monomer, and we get a covalent bond here between those two. So now we're building a polymer. So this could be two amino acids bonded together here to form the building blocks of a protein. So this covalent bond, what would the name of it be? Special kind of bond that we find in proteins. Do you remember? Starts with a P. Peptide bonds. Yeah, peptide bonds. So we call that dehydration synthesis. Right in the name, you can figure out the answer. So if you're on a test and I talk about the what happens in dehydration synthesis? Well, if you're dehydrated, what's happening? Are you losing water or gaining water if you're dehydrated? You're losing water. Can you see a loss of water over that arrow? Yeah. Synthesis. If I synthesize something, am I making it or breaking it down? To synthesize. You're making it. Synthesis means to make. Okay, so I'm making something by removing water. Simple enough. And hydrolysis is the opposite. If I bring in my Snicker bar, and I bring in a protein, for example, here. This is a polymer made up of more than one monomer. So this is my protein, couple of amino acids. With the help of adding water, I can break that covalent bond and add an OH and an H here, and I have two separate amino acids. So we call this hydrolysis. Lysis, think of it means to slice and dice. It means to break something apart. Hydro means water. So you are bringing water in to break something down, and that's what hydrolysis is. So here's an example with an organic molecule. We have glucose and fructose at the bottom there. Those are two monomers, and we are going to, if we go to the right side, we're going to remove water and link them together. So what do we call that process? The top arrow? Yeah, dehydration synthesis. Again, synthesize. We made something by removing water. And then, if we have sucrose, look at it from the other direction, we're going to, let's say a plant is making that sucrose, okay? Let's say we're going the other direction, and we're going to come back and break that sucrose down in our digestive tract. What do we call that process that consumes water? Hydrolysis. So did you ever have like chocolate cake, and what's the best thing that goes with chocolate cake? Milk, right? Because you get thirsty. That process of breaking down all that sugar pulls water from our system, from our mouth, our tissues, and we feel thirsty after that. Just like when people drink Mountain Dew, oh, I'm thirsty, I'm going to have a Mountain Dew. That Mountain Dew tastes great when it's going down, right? It wets your mouth, you feel like you're getting hydrated. But about an hour later, you're like, oh, I'm really thirsty, right? Because of all that sugar in the Mountain Dew pulled water from your tissues and actually is creating more thirst. And what happens is teenagers and young people and even older people get into this cycle of drinking way too much sugary soda all day long because they think they're quenching their thirst when actually they're creating thirst. And they're bringing in a lot of calories. If you look at the amount of sugar in Mountain Dew and the non-diet sodas, there's just a lot of sugar in there. And if you're not running marathons to get rid of that, not marathons, but exercising every day to get rid of that excess sugar, that's just turning to fat. And a lot of people struggle with obesity simply because they drink sugary sodas. So with our kids especially, that's a really easy way to help our kids stay on the healthy side of their weight is just by eliminating sugary drinks, because kids are famous for that. They don't like water. They like the taste of the sugary drinks. And then that leads to more thirst, which leads to more sugary drinks, and the vicious cycle continues. Okay, so our first organic molecule we're going to talk about are the carbohydrates. So carbohydrates are the major energy source for our cells. So when you think about the importance of carbohydrates, it's energy, quick energy. They pass through the system really fast. So if I have, say, a candy bar or a piece of white bread that is a lot of just refined sugars that makes up that bread, I'm going to be hungry an hour later. There's still a lot of calories in that white bread, but it didn't keep me full. So then I go looking for more food. And that's another vicious cycle that we get ourselves into when it comes to carbohydrates. they're a quick source of energy. They make us feel better right away, but they pass through our digestion so quickly that they don't stay in the stomach very long, and then we feel hungry right away again. So that's why proteins and fats added with carbohydrates help us stay full longer, and we're not always looking for more food again. Again, kids end up with the cookies and the candies and the chips that burn through their system, and they end up snacking all day and not being satisfied, and then again leading to obesity because the calories are still there. So monosaccharides, mono means one, di means two, poly means many. So if we look at the monomer, which is just a single sugar unit, so the glucose, all of these are monomers. You can see they're not bonded to anything else. They're just single units. So these are called monosaccharides. When I bring these into the body, they're absorbed very quickly into the blood and used for energy in our cells. So all of our digestion, when we bring in carbohydrates and even fats and proteins, can be converted to glucose, because glucose is what our cells recognize, and they can transport glucose into the cell very quickly. So glucose is the number one monosaccharide needed for energy to make ATP. Very important organic molecule. And it's a monosaccharide, one single unit, quickly absorbed. If I take two monosaccharides, bond them together, what process would that be called if I bond two monosaccharides together? Dehydration, synthesis. Good. Then I would get sucrose in water. Sucrose is table sugar. This is what we sprinkle on our foods. This is what tastes good. We're born with a desire for sugar. When they have to circumcise infant, newborn males, they give them a little sugar water rather than a pain reliever, and they find that that's just as good as relieving their pain and distracting them, as a pain reliever would. So we are born with a taste for sugar. So sucrose is a disaccharide. Maltose, lactose are also disaccharides. Lactose is something that we find in milk. It's a milk sugar. And some people, as they age, or even some people are born this way, they're lactose intolerant, which means they lack the enzyme to break this bond between galactose and glucose. So normally we have an enzyme, lactase, in our digestive tract that when we eat ice cream or milk products, cheese products, we can break this bond and release those sugar units, and they're absorbed into our blood, no problem. But if you lack that enzyme, what happens is this lactose sugar ends up in the large intestine, and it's not supposed to be there. Our large intestine is like, what are you doing here? You were supposed to be digested way up in the system. So now the digestive tract, you get gassy, diarrhea, bloated. Some people even get sick to their stomach, nausea, vomiting earlier on. So lacking that enzyme can cause a lot of upset. So how do we get around that? Some people take the enzyme lactate when they have dairy products, or some people just avoid dairy altogether. Some people have milk allergies where they get even more reactions to the presence of that lactose. But it's a disaccharide, and we need to break that bond down to release those monomers so they can be absorbed into the digestive tract. The key thing to keep in mind is these bonds need to be broken if we're going to absorb them into the blood and use them to make, again, things on this list. So all of these things need to be digested. Bonds need to be broken to provide the energy and the building blocks for making these important organic molecules. So what would be this process here? We're going to make, digestion, like in the case of lactose. What process is lacking in people that are lactose intolerant? Hydrolysis. Hydrolysis of the lactose, right? Because they can't break that lactose down. The enzyme is missing. So polysaccharides, we said poly means many. So that is a good source of energy. This is going to take a little longer to pass through our digestive tract because it's going to take time to get rid of all those bonds. So if we look at an example, look at all those repeating sugar units. This is glycogen. This is a storage molecule in animal cells. So we store extra sugar as glycogen, and as needed, the job of the liver is just to release bits of glucose a little bit at a time to serve our needs. For example, if a person is a runner or an athlete training for a long aerobic event, like a basketball player, sometimes they do carb loading the day or two before, right? Because they want to bring extra sugar in, fill the glycogen stores in the liver and muscle cells So the next day when they're competing in that event and they're not eating, there's a form of energy, and those sugar units are released little by little to make ATP and keep those muscle cells functioning. So glycogen is the storage polysaccharide for animal cells. In plants, it's starch. And we can digest starch, right? We go to plants like potatoes and corn for the starches they have, and we get energy from those polysaccharides. And again, they pass through the system very quickly. If you have a diet just on, rice and pasta and potatoes, you're going to be eating a lot of it because it makes you hungry again, because it is processed quickly. Not as quickly as sucrose, right, or definitely not glucose by itself, but it does have a little more energy, but not as much as a fat or a protein. And we'll talk more about that when we get into the nutrition study later in the semester. So starch is a storage polysaccharide for plant cells. The plants make it and use it for energy as well, and we use it when we eat plants. And then cellulose is the other polysaccharide, also found in plants, but that's a structural polysaccharide. It's found in the cell walls of plants, and that's what allows plants to stay upright. If plant cells didn't have cellulose, then all the plants would wilt and they wouldn't have any structure to them. And that's what gives you the crunch, right? When you eat a carrot or spinach, green leafy vegetable, the cellulose in there is what we call roughage. We can't break the bonds between the carbohydrates in cellulose. So we call that roughage. When it passes through our digestive tract, we chew it up, it stays in our digestive tract and adds bulk to the stool and keeps people regular. So it's important that for the digestive tract that we have cellulose, but we don't get the energy from those sugar molecules. It just passes right through and keeps, like I said, bulk to the stool and prevents constipation. So the next category of organic molecules are lipids. Another name for these another name for lipids, fats. Yeah, these are the fats. So these contain a lot more energy, takes more energy to break these down. They keep us fuller longer. Again, they all contain carbon, hydrogen, oxygen, but not as many as we see in carbohydrates, and sometimes we see phosphorus in there. But again, I'm not going to hold you accountable to the individual types of atoms in these organic molecules. I kind of just want you to know their basic functions and basic structure. So there's 4 different types of fats, and you do need to know the 4 different types of fats. So triglycerides, phospholipids, steroids, and eicosanoids. Lipids are nonpolar. They're non-charged molecules. They don't dissolve in water. I can throw sugar in water and it'll dissolve. But if I throw fat in water, it won't dissolve. Bacon grease in your pan, you always have to add a little soap, right, to get that bacon grease to break down and dissolve. So fats are stable molecules. They do not dissolve in water. Some important lipids that we see in the body are sebum. Sebum is produced by oil glands in our skin, and it helps hydrate the skin. As we age, our oil glands become less active and our skin becomes much drier. Myelin is another fatty substance I mentioned earlier. That's one that insulates our axons and speeds the conduction of nerve impulses. People with multiple sclerosis have demyelination on axons in the brain and spinal cord. And if you've ever heard of Guillain-Barré syndrome, that is where we see demyelination in the nerves coming from the spinal cord out to the extremities and the organs. So demyelination of nerves outside the central nervous system we call Guillain-Barré, and demyelination in the central nervous system is multiple sclerosis. So that's an autoimmune disease. Guillain-Barré sometimes caused by a virus. Sometimes it gets better. Sometimes it causes permanent disability. It's one of those really strange diseases. Okay, so looking at, if you tap on the screen, a person will talk about this picture, but we don't need to listen to her. I'll just explain the basics. But this is a triglyceride. Tri means 3. So where it gets its name from is there's 3 fatty acids, right here, 3, with a glycerol backbone. And if you look at it, can't you kind of see the letter E? If you go like this, and then here's the middle line for the letter E. So there's 3 fatty acids with a glycerol backbone. And these are what we call body fat. So the fats we get in our diet, animal fats, butter, lard, bacon grease, the little white spots you see in raw hamburger, those are all triglycerides. So we can take any calories we bring in through our diet and make triglycerides and store that fat under the skin. So you can see people that get to be like, what is the show on TV, My 1,000-Pound Life, right? Isn't there 600? Oh, isn't it 1,000 pounds? Somebody, so we're not quite there yet. But there are people in the Guinness Book I know that are 1,000 pounds. So we have gotten that large. I mean, those organs are so taxed by maintaining that body mass. But we have an ultimate ability to make triglycerides. We can just make more and more and more and more and more, and we don't lose that unless we start burning energy and needing it for energy. So people have the ultimate ability to get bigger and bigger and bigger. So what else can I say? That's it for that. So there's two different types of lipids, triglycerides, that we see in the body. There's unsaturated and saturated fats that we bring in as nutrition. And like I said, energy storage, insulation, the more fat you have in the body, the more insulation you have. People tend to be heavy. People who are heavier tend to sweat more when the temperatures get higher because they have more insulation. Less fat on the body, less insulation. And a good healthcare application to that is anorexia. Anorexia is where people don't eat. And as a result, they lose all this body fat, all this adipose tissue, all these triglycerides that are meant to be under the skin for cushion and insulation. And as a result, they have no ability or less ability to regulate their temperature. They have less insulation to keep them warm. So how does the body respond to that? The body grows hair over those areas. So if you're looking at a young person or anybody that you think might have anorexia, take a look at their arms, look at their back. If they have more hair growth, that's the body's way of making up for that less insulation because of the less fat on their body. And as we age, we lose that insulating layer in the hypodermis, those triglycerides in the skin. And that's why when you go to the nursing home, those of you that work in a nursing home, you know, it's 85 degrees in there, right? So if you move at all, you're dripping with sweat. But then your resident is asking you to hand her a sweater. So that's just because they have less insulation, less body fat. So saturated fatty acid, what makes them saturated, what makes them solid at room temperature. So when you look at raw burger, for example, it's got the white spots, right, in the burger, and then you put it in the pan and it heats up and then it melts and you've got the grease in the pan and then just the burger left. Well, what keeps that triglyceride solid at room temperature is the presence of single covalent bonds between the carbon atoms. So if I look at the fatty acids there's single bonds in a saturated fatty acid. That makes them solid at room temperature. And unsaturated fatty acids have double bonds in between the carbons, and those are liquid at room temperature. So those tend to be our healthier fats. But now we've taken some oils and made them solid at room temperature, like some of the butter spreads that you see that are not real butter, but they're supposed to be healthier for you, less calories, but they contain trans fats. And trans fats are not processed by the body, and they contribute to high cholesterol. So margarine, I grew up where margarine was the big thing. Oh, don't get butter, use margarine. Margarine is worse for you and more unhealthy for our heart than butter is. So we've really kind of gone away from that, and now there's alternatives to this trans fat process. But what you want to look for in your ingredients on the back of your tub of spreadable butter, low-fat butter, is partially hydrogenated oils. Partially hydrogenated is a trans fat. So you shouldn't see those words in your ingredient list if you want to have a healthy butter spread. Omega-3 fatty acids are healthy fatty acids. We need these fats because, again, myelin is a fat, right? The sebum in our skin is a fat. Sex hormones, we're going to discover, are fats. Other hormones we have in the body are fats. So we need fats to make these healthy lipid molecules for our metabolism and homeostasis, but we want the healthy version. So fish oil is an example of an omega-3 fatty acid. And fish oil has the benefit of being heart healthy, and they found that it reduces inflammation and causes a slight thinning of the blood. It almost acts like a weak ibuprofen. So people that take fish oil every day, and also they find that it also helps brain function. So fish oil is a great thing to add to your diet if you don't have a diet high in these healthy fatty acids, because it has multiple effects in the body. Omega-6 fatty acids are the bad fatty acids, like I say, the saturated that we find in chips, pizza, donuts, cookies, all the stuff that, we go to Quick Trip. And my husband worked at Quick Trip, and he said the junk that people buy, it's just want bags of chips and cookies and beer and cigarettes and tobacco, and that's all they bring to the, it's like, what are we doing to ourselves? Everything in moderation, right? But typically, if a person feels tired, achy, lethargic, moody, and their diet is high in chips and pizza and burgers and fast food, a lot of that is diet related. It really is. You would be surprised on people that have changed their diet and gone to healthy fats, how they're less achy, less headaches, more energy, better moods. But you don't know until you try it. So you always have these people that tell you to eat better, right? But unless you've really done it, you don't know the difference in energy levels. So think of just even making a simple choice to add maybe a fish oil, a healthy fish oil, capsule to your morning routine. Take it with food because they can be kind of fishy tasting. I have some that are orange flavored, so you don't get the fish burping that sometimes happens when you have fish oil capsules. Otherwise, there's healthy forms of, using olive oil, and nuts are good sources of healthy fatty acids. There's some really good cereals out there. But anyway, so back to triglycerides then. So there you can see the function. Take glycerol, 3 fatty acids, makes a triglycerol. And again, removing water, right? Removing water in the process. So that is dehydration synthesis. You're taking 2 smaller things, 3 individual fatty acids, a glycerol molecule making a bigger thing. So phospholipids, you've heard of these. They're part of the cell membranes. You recognize that far right-hand structure from general A&P? The little head, the phosphate head, and the fatty acid tails. So these are what make up our cell membrane. So again, we need fats in our diet because our cell membranes are made up of fatty acids. We have to have those in our diet. Steroids are a type of lipid, and they consist of cholesterol. So the key thing that determines if something is a steroid is the cholesterol backbone. So if we look at this structure here, we can see the 4-ring structure. This is cholesterol, but then when we add some other carbons to it, we get the different organic molecules that are classified as steroids. Some steroids that we see in the human body that are really important for homeostasis. A big one is vitamin D. Another name for vitamin D is calcitriol. And vitamin D, can anybody name any functions of vitamin D that you've heard of? We need it. Helps your bones stay strong. What it does, it helps us absorb calcium from the digestive tract. So vitamin D is kind of an escort for calcium to get it out of the digestive tract into the blood and into our bone to keep our bones hard. Yeah, vitamin D is such a unknown molecule because what we do know is that most cells of the body have receptors for vitamin D. So we know it's not just bone that needs vitamin D. We know that people with low vitamin D levels tend to have depression, low immune function. So we used to say, we should limit our vitamin D to 400 milligrams. Now they're putting people on as many as 10,000, I don't know what the unit is, not milligrams, MIU or whatever, of vitamin D. So it's something that we should always check to make sure we're at the right dosing, but we're not very good at dosing it. And 80% of Americans, they say, are deficient in vitamin D. We make the precursor for vitamin D in our skin in the presence of sunlight. So people that live in sunnier areas where they're not inside as much, unlike in the Midwest in the middle of February or January, they tend to have higher vitamin D levels. Like they found just a half an hour in the sun can make 10,000 MIU of vitamin D. So sun does a lot for mood, right? We know that. Getting outside in the sunshine makes a difference. So if you or someone you know struggles with depression, adding a vitamin D supplement is something to consider as a natural way to fill a deficiency. So often in our society, we tend to just throw pills at the symptoms, right, rather than find the cause. Sometimes vitamin deficiencies can be a cause of illness or disease. So cholesterol then. Where do we get cholesterol from? 80% of the cholesterol we need to make all these steroid molecules is formed by the liver. So cholesterol is made by the liver. We only need like 15% from our diet. We get way more than that. If you're a meat eater or a dairy person, you're getting these fats, this cholesterol through your diet, way more than you need. So that some people are better at processing excess cholesterol and washing it out of the blood and metabolizing it in the liver. Other people are not as good. They don't produce the right lipoproteins, the HDL, to clean up the vessels from extra cholesterol, and they end up with hardening of the arteries and narrowing vessels, and that leads to heart attack and stroke. So cholesterol is important. We need it for our cell membrane. That phospholipid bilayer is liquid, but a little bit of cholesterol inserted in there stiffens that membrane and keeps it intact. So we need it for our cell membranes. We need it to make important hormones, and some of those hormones are estrogen, that makes women women, those secondary sex characteristics, testosterone, the male hormone that makes men men and contributes to sperm production, and two other ones. Cortisol is a steroid. It's a long-term stress hormone, and it also has anti-inflammatory properties. So sometimes people will get cortisone injections. Have you heard of that? For a bad knee or bad hip or bad back, because it reduces inflammation. And another one is aldosterone. Aldosterone is a hormone produced by the adrenal cortex that that increases a falling blood pressure. So that's another steroid hormone. So we need these important steroids. When you think of steroids like, the neighbor kid is on steroids, what is that? That's testosterone. They're taking testosterone to cause more protein synthesis, bigger muscle mass, because testosterone promotes protein synthesis and greater muscle mass. So that's what the hormone is. It's just testosterone. So you can identify a steroid by looking for that cholesterol backbone, the four-ring structure. Eicosanoids. Eicosanoids we're not going to talk a lot about, other than prostaglandins are a group of chemicals that are fatty. They're lipids, but they have a big role in the body. If you look at control of blood pressure, blood clotting, inflammation, labor contractions. So they have a purposeful role, but when they build up in the tissues, it causes pain. That's a side effect of prostaglandins, is they cause pain. And lastly, well, almost lastly, third one out of our four, proteins. Proteins make up a lot of our cell mass in the sense that they're structural. They're not just a chemical in solution, but it's what we're made up of. So our bones are made up of protein, collagen. I mentioned that. Our skin is made up of protein, collagen, keratin. Keratin is the protein that is a waterproofing protein. It gives us kind of a waxy layer, keeps the inside in and the outside out. So that's an important protein. Actin and myosin, if you remember that from general A&P, those are those contracting proteins that interact to form muscle contraction. Troponin is another enzyme that is a protein that is involved in muscle contraction. And when muscle cells, like heart muscle cells, are damaged, like as in a heart attack, the troponin enzyme is present in the blood. It shouldn't be in the blood. It should be in the muscle cell doing its job in the heart. But when the muscle cells of the heart are damaged, it releases troponin into the blood. And that's an indicator that doctors use, that they'll draw, the MLT will draw a troponin and see if that is elevated, because it should be like 0.01. If a person has had a heart attack, then it might be as high as 4 or 5 or 6 or higher. It could even be less than that and still indicate a heart attack. So if you or someone you know is thinking, did she have a heart attack or did he have a heart attack? Say, what was the troponin level? Did they check a troponin? That's an early indicator of a heart attack. Okay, so remember that the polymer is a protein, so it's like a pearl necklace. We call the necklace the protein, and the individual monomers that make up that protein are amino acids, and they're bonded by peptide bonds. And the unique thing about proteins is they have a very specific shape, and that shape determines their function. If we change the shape, we can change the function, which is not good. So proteins are sensitive. They're sensitive to radiation, heat, excess cold, acids, bases. So if you look at a typical protein, there's two parts of it. There's an amine half and an acid half that has the COOH arrangement. We're not going to get a lot into the chemical structure, but you should just recognize it structurally, that it has this half and this half. All amino acids are the same, except for this R group is what varies from one amino acid to another. So there's 20 essential amino acids that we need in the human body, and they all differ just by this. So what's in the brown oval here is the same with every amino acid. It's this that differs from amino acid to amino acid. So again, taking two amino acids, putting them together is a dehydration synthesis, forming a peptide bond there with the removal of water, and the opposite going in the other direction. Hydrolysis, where we're adding water and separating or breaking that peptide bond. So there's 4 levels of structure. I'm not going to hold you accountable for the details of this. I don't think this is relevant to how we care for our patients. Just know that the order of amino acids is one level of structure that's important. And then how those amino acids interact with one another is another level of structure that's important, and that's the hydrogen bonds between the different levels of the amino acids, or different types of amino acids. And then it folds in on itself, and there's other intramolecular forces that fold it in to give it a tertiary structure. And quaternary structure is when you have different parts of the whole compound that form a specific protein. Not all proteins depend on this level of folding in order to work, but an example of a protein that needs that level of folding to be just perfect and just right is hemoglobin. Hemoglobin is a protein that transports carbon dioxide and oxygen in the blood, and it has to have this very 4th level of structure, this quaternary structure, in order to function properly. People with sickle cell anemia have damaged quaternary structure because of a change in an amino acid. So if we go back to the primary structure, if I change an amino acid, that's going to change how that amino acid interacts to provide the secondary structure, which affects the tertiary structure, which affects the quaternary structure. So in low oxygen environments, people with sickle cell anemia, their red blood cells kind of warp, and they don't pass through the capillaries, and it causes clotting throughout the system, and they don't get blood flow to their extremities, and it's very painful. So they have to really be careful with their oxygen if they're traveling to high altitudes or exercising, or if they have bad lungs due to emphysema. They need a little more oxygen because they can get in a sickle cell crisis, which can lead to death eventually. So it's a serious disease, and it's an inherited disease that we'll talk about later in the semester, or in a couple weeks when we study genetics. So this is just a little review. You can tap on that if you want to, if you pull these up on your computer, about protein structure. 2 major categories of proteins. So we had 4 different types of lipids. There's 2 different major categories of proteins. There's fibrous proteins, which are structural, and there's globular proteins, which have more of a function associated to them. So fibrous proteins are those that, like I say, give structure to the body. We talked about keratin in the skin, waterproofs the skin, gives you that waxy layer. Elastin gives flexibility to our connective tissues, allows them to bounce back when they're stretched. Collagen is the most abundant structural protein in the body. Like I said, we find it in a lot of our connective tissues in the skin. We find it in ligaments and tendons. We find it in bone. And then contractile fibers, we already mentioned those, actin, myosin. Those are examples of fibrous or structural proteins. Globular proteins are those that have very specific shapes. So some of them are going to exhibit that quaternary structure in order to function properly. And some of those include antibodies. So when you are exposed to some type of foreign body, what you call an antigen, you form antibodies. And the most common abundant antibody is IgG. So that's an example of a globular protein. So if you have a patient who has no appetite and is sick with an illness, low immune system, maybe they had surgery, so they had damage to structural proteins as well, right? So they need to heal. They need to build more structural proteins, collagen, right, to heal and span that incision. And then they have underlying disease, low immune function, and now it's time to order off the menu. What do we need to make these proteins? What does the body need to make new proteins? What has to come in from the diet? What? Protein. Yeah, protein. So when they say, I'll just have some strawberries, is that a good choice? And say, oh, you're healthy, you're ordering strawberries, good choice. If you don't know your advanced A and P, you might say that that's a good choice. And some oatmeal. I'll have some strawberries and some oatmeal. Is that enough to help heal and make more antibodies to fight infection? No, they need protein. And that's one of the biggest things, if you guys are nurses' aides today, that you can change tomorrow. Now that you know this, make sure your patients are ordering some protein on their menus. Say, well, let's talk about some protein. And one thing that my experience, people with a poor appetite and not a very good digestive tract, what they tend to like that are good protein sources are yogurt, cottage cheese with peaches, and like a hard-boiled egg. Those are things that the elderly eat that are palatable when they're not feeling well. When you say, how about a pork chop? No thanks, right? But even an omelet, oh, no thanks. Cheese, no thanks. When you're not feeling well, those things are not very palatable. But yogurt is a good one. So we need protein to make protein. Other proteins that are important, insulin is a very important protein. It helps lower our blood sugar. So we need that protein to keep our blood sugar stable and prevent blood sugar spikes. Cytokines and complement are two types of proteins that help our immune systems function. Cytokines activate the immune response. Complement promotes inflammation. EPO is another protein produced by the kidneys. When oxygen levels get low, it tells the bone marrow to make more red blood cells. Have you ever heard of blood doping before that some of the athletes were using? So they were removing some of their blood, stimulates the kidneys to produce EPO. The bone marrow makes more red blood cells, so now when they go to perform in their activity, they've got more red blood cells than the person next to them who did not blood dope. But now they're doing testing for that to make sure that people aren't doing that. They're actually measuring their hematocrit, their blood, the number of red blood cells they have in their blood, and they can't be different, during training and the time of when they perform. So we're trying to prevent that. Troponin I already talked about. Surfactant I already talked about. These are all globular proteins. And another one is renin. Renin is a protein-like substance that the kidney cells secrete when there's less stretch in the blood vessels leading to the kidney, and as a result, it raises blood pressure. So renin is a protein released by the kidney to raise blood pressure through a series of reactions, and we'll study that later on when we get into the urinary system. So because structure is so important to protein function, denaturing is an example of, or is a process in which we break protein structure. So to denature a protein means you're changing the structure, and that can change the function. So there's a number of things that can cause denaturation. Simplest example you can think of, next time you cook an egg, that egg yolk is a protein. When you add heat to it, it becomes solid white. You can't go back and get that slimy, see-through egg yolk, or not egg yolk, egg white again. It's been denatured. That protein is completely different structure, different appearance. And that can happen in our bodies as well. We can have permanent reversals of tissues that we can't bring back because the proteins in that tissue have been denatured by a burn, for example, a chemical burn. So enzymes, the key thing to know here is that all enzymes are proteins. So if it's an enzyme, it's a protein. So all enzymes are proteins. And we can proceed with all of our metabolic reactions in the body at 98.6 because of enzymes. Enzymes lower the energy for reactions to occur, and because of enzymes, we can maintain at 98.6 and not have to have a higher temperature to maintain that same metabolism. Now, what happens, again, to proteins if we raise the temperature? They denature. So if we have these enzymes that are, producing neurotransmitters and keeping our homeostasis in check, and we get a fever of 106, that is going to denature proteins, and that's going to affect metabolism and nervous system function. And a symptom of a really high fever in kids especially is being lethargic, being really, really sleepy. So it's always important to watch kids that are getting a temperature as bedtime approaches, because we know that temperatures rise through the night, and there have been unfortunate incidents where parents have had a baby, say, toddler, a 2-year-old or 1-year-old with a fever of 100, 203, and they say, well, let's just see how it works out in the morning and just put baby to bed, and baby passes away overnight of a febrile seizure. So if you have a child that's going to bed with a fever over 101, and you're not treating it and seeing that fever come down, then you should keep that child near you so you can check on the child throughout the night and make sure that fever is not climbing, because that's going to change the proteins in the body and could lead to death, seizures and death. I know someone in our community that happened to, actually. Child was sick, tucked the little boy in bed, and the next morning he had passed away through the night. Perfectly healthy child, just had a virus and had a febrile seizure through the night and passed away. Very, very sad. Okay, so enzymes, I want to just refer you to this diagram. I'm not going to go into a lot of detail on enzyme activity, but you should know that the substrate is whatever chemical we're acting on. So if I bring in a cracker that's full of starch, starch is the substrate, and an enzyme is going to act on it. And the enzyme in our saliva that acts on starches is called amylase. So enzyme E here would be amylase, that when that starch, in this case it's amino acids, but starch is what? What is starch, did we say? Carbohydrate. What type of carbohydrate? Mono, di, or polysaccharide? Do you remember? Starch. Is it a simple carbohydrate or is it a long storage? Yeah, so it's a poly. Poly means many. So it's a polysaccharide. So when it bonds to the enzyme is going to break those covalent bonds between those carbons in that starch and release, well, this one's going the other way. This is too bad. Okay, well, I can still use my example. And then it would break those bonds and release those little sugar units, and that can be digested then. The example here in this slide is taking 2 amino acids, interacting with the enzyme, and that enzyme is forming a peptide bond, releasing water. Again, so this is what? Dehydration, synthesis, dehydrating, losing water, and forming something bigger, which is a dipeptide, or 2 amino acids bonded together. So the enzyme, does the enzyme change in the process? No. So enzymes are found in small amounts in the blood. They don't change in amount because they can be used over and over again, but they're very specific. Notice that active site has to exactly match the molecular structure of the substrate of those amino acids in order for that reaction to occur. So enzymes are very specific. And then lastly, DNA and RNA. We're going to talk about this a lot in lab, so I'm not going to belabor this too much. But the key thing you need to know is the building block of DNA and RNA are nucleotides. And a nucleotide is made up of a phosphate, a sugar, and a nitrogen base. So there's 3 parts to a nucleotide, and we see repeating units of these 3 pieces that makes up DNA. So 1/2 of the DNA molecule contains nucleotides with a specific nitrogen base arrangement, and the other half has a complementary arrangement of nitrogen bases. And again, we're going to talk more about this in lab, so I don't want to belabor this. We've been sitting a long time here. But the key thing to know is that the DNA molecule is a double-stranded, twisted ladder, and the purple and the light purple on the side are phosphate and sugars, and the sugar in DNA is deoxyribose. And what forms the rungs of the DNA ladder are these nitrogen bases. RNA is similar, except the sugar in RNA is ribose. Thymine is a nitrogen base in DNA. We replace that with uracil. And it's a single-stranded molecule. So here's DNA, and RNA is single-stranded. So we only see basically like 1/2 of what we would see in a DNA ladder. So here's the nitrogen bases going down the center, and we'll talk more about those in lab. And lastly, ATP. This is the fuel for our cells. So you go to the store, you go to the gas station, you give them money to give you gas, and gas is what helps your car go, right? So when we think of cells, what helps our cells transport substances across the membrane, contract our muscles, that movement of structural proteins and movement of substances across the membrane is because of ATP fueling that process. I can't stuff dollar bills into my gas tank and make my car go, right? So the dollar bills is like glucose. We need glucose to come in to make ATP through the process of metabolism, and that's next week's topic of how we go from glucose to ATP. So for now, what you just need to know is that glucose is the energy, is the fuel that starts the process to get ATP, but ATP is the energy currency of our cells. It's what our cells directly use to get energy. And what's special about ATP are these little red bonds between the phosphates. So there's energy. Think of these like a coiled spring that when I break these bonds, I release the energy there, and that fuels a process. So we take a phosphate from ATP and we add that phosphate with that special bond to another molecule. We call that phosphorylation. If I remove a phosphate, like if I remove a phosphate from ATP, we call it dephosphorylation. So we can move energy back and forth. When we form ATP, we're storing energy. When we break ATP down, we're releasing energy. So there's ATP, which means how many phosphates? 3. Then we have ADP, 2 phosphates, AMP. Which has the least amount of energy of these 3? AMP, right? Less phosphate groups. And which one has the most energy? ATP, okay? So basically ATP, the structure, is the amino acid adenine bonded to a ribose sugar that we see in RNA with 3 phosphate groups. So that's ATP. So this is a reversible reaction. Again, when we're going to the right, when we're breaking down ATP, we're releasing energy. When we're forming ATP going in this direction, we're storing energy. And again, it's a dehydration, synthesis, and hydrolysis reaction. So in summary, looking at these major organic molecules, whether it's proteins, lipids, nucleic acids, or carbohydrates, there are certain foods that are rich in these molecules. So if a person wants to have a healthy blood sugar, let's say they have insulin or they're getting close to being diabetic, they have pre-diabetes, they don't want to have excesses of carbohydrates, because if you look on your right-hand side, my left, you can see obesity, diabetes, cavities, intestinal irritation, high triglycerides if we have too many carbohydrates in our diet. So we really have to watch our balance of these nutrients. And then if you don't have enough, then obviously you're not going to have enough energy to fuel your processes, so the body burns fat. And when the body burns only fat for energy, it causes acids to be produced. And we'll study that with metabolism next week. Have you heard of ketoacidosis? Or people that go on the Atkins diet, that they eat eggs and bacon, and my brother and my husband both did this years ago, and they lost like 20 pounds. But all they ate was fatty foods and no carbohydrates. Because if you don't have any carbohydrates, your body is primed to go after fat to get the energy it needs and make glucose from that. And we'll study that next week. But not good for the body long term. It's very hard on the kidneys. Again, lipids, we can see there's different types. Omega-6s, omega-3s. Like I said, we have to be careful with some of those omega-6s because they promote inflammation. Omega-3s are the better ones. And then the proteins. So there's complete proteins and incomplete proteins. Who has to worry about proteins, do you think? What type of person out there with a what? Vegetarians, yeah. They really have to be careful that they get enough protein in their diet because animal proteins are complete proteins, but vegetables and seeds are incomplete proteins. So they have to combine certain proteins to make a complete protein to get enough of those amino acids that are necessary for life. Like I said, there's 20 essential amino acids we need for life. We need to get those in our diet. The pieces anyway, and then we can assemble them. Okay, we will see you in lab at, let's see, we could probably start